Okay, hi, this is my Lab 6 magnetic braking, and my name is Megan Coffey. So, for the introduction, the purpose of this lab was to observe how the magnetic field of a bar magnet interacts with and induces a current in a conductive tube of aluminum foil, and then we created a computational model of this interaction to compare it with the observed results. So, the main physics principles we used in this lab were Faraday's law, Lenz's law, and properties of magnetic fields and forces paired with Newton's third law and the PHYS2212. By the end of this lab, we measured an average time of 1.114 seconds for the bar magnet to fall through the aluminum tube, but the computational model calculated a time of 1.332 seconds. So these are the models and physics principles. We had Faraday's and Lenz's laws. They state that a change in magnetic field creates an electric field, which induces a current to produce an EMF. And then magnetic fields and forces, we have a magnetic field that is changing, which induces a current in the aluminum foil. And then the Biot-Savart law, which we see like the derivation that we used in this one, describes the magnetic field at a point due to a ring of current. And then Newton's third law states that basically the magnitude of the force on the magnet is the same as the magnitude of the force on the foil. So in this experiment, we let a bar magnet fall through a conductive tube of aluminum foil in order to induce a current by changing the magnetic field. We then created a computational model of this using GlowScript. We assumed that the magnetic field of the bar magnet is the only magnetic field acting on the tube of aluminum foil, and the bar magnet can be treated as a magnetic dipole and air resistance is negligible. And then the system is the bar magnet and the surroundings are the aluminum foil and everything else. Initial conditions are that the current magnetic field of the aluminum foil are 0. So for this procedure, we basically just held a conductive tube of aluminum foil vertically upright and dropped a bar magnet with the north end facing up into one end and watched it fall at the other end. We took a video of this and repeated it 5 times. This is the data that we collected for the 5 trials. This averages out to 1.114 seconds. So then for my code, first of all, I adjusted all the measurements to match our experiment, and then created the magnetic field formula down there in step 2. And then step 3, calculate the magnetic flux, calculate the current in the ring, and then calculating the B field at each ring, basically through the tube, and then gravitational force and magnetic force, and then total force, and then magnet velocity position. And then this was basically the graph that it came up with, and it calculated a time of 1.332 seconds. So this 1.332 is a little bit different from our 1.113. There are many possible sources of error. There could be human error in calculation of timing or in holding the tube not perfectly vertical and perpendicular with the floor. And then it could also be because air resistance was not accounted for. So what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So because of Ohm's law, a smaller resistivity equates to a larger current. Therefore, there would be a larger induced current in the aluminum tube, which would increase the magnetic force and slow the magnet down, basically increasing the time it takes to fall through the tube. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Basically, this would disrupt the current going through the rings, which would result in a smaller amount of time for the magnet to fall through the tube. So in conclusion, we used Faraday's law and Lenz's law to observe how a falling magnet affects the magnetic field and current in a conductive tube of aluminum foil. And after 5 trials of the experiment, we determined that it took an average of 1.114 seconds for the magnet to fall through the tube. And then after creating a computational model of the experiment with GlowScript code, it was calculated to take 1.332 seconds for the magnet to fall through the tube. Thank you.